This next step, highlighted here as HW/SW co-verification, is one of the most critical stages in the entire SoC design flow. It's the moment of truth where the hardware and software designs, which have been developed in parallel, finally meet. The co in co-verification simply means together. We are verifying both components at the same time. So, let's back up for a second. On the left side of our flow, the hardware team has integrated the necessary IP cores and run functional simulations to ensure the hardware logic itself is correct. On the right, the software team has been writing and integrating software drivers and running their own simulations, perhaps on a computer model of the hardware. And in the middle, we've created a prototype of our hardware, often using an FPGA. Now, HW/SW co-verification is where we take the actual application software and run it on that hardware prototype. Why is this so crucial? Because many problems only become apparent when the hardware and software interact. A hardware block might pass all its individual tests, and the software might seem perfect in simulation, but when the software tries to write to a register in the hardware, does it work? Does the timing match up? If the software expects a response from the hardware within a certain time, does it get it? These are the kinds of issues that co-verification is designed to uncover. Think of it as a dress rehearsal for a play. The actors, software, have learned their lines, and the stage crew, hardware, has built the set. But you don't open the show until you've had a full rehearsal with the actors on the set to make sure they can move around properly. The doors open when they should, and the lights work on cue. That's what co-verification is for our SoC. This step is a massive risk reduction effort. Finding a bug at this stage, where we can still modify the software code or the hardware design on the FPGA, is relatively easy and inexpensive. Imagine finding that same bug after the chip has been manufactured. It would be a disaster, costing millions of dollars and months of delays. As you can see from the diagram, successfully passing HW/SW co-verification is the final gate before we proceed to volume manufacture and ship. This means that only after we are confident that our hardware and software work together flawlessly do we commit to the expensive and irreversible step of fabrication. This entire design, integration, and verification process falls under the responsibility of the fab's vendors, whose primary job is to deliver a correct and verified chip design to the foundries for production. After all the rigorous testing, simulation, and co-verification, we finally arrive at a critical, high-stakes phase in our SoC design flow, volume manufacture and ship, which is highlighted here. This is the moment where the digital design becomes a physical reality on a massive scale. Up to this point, the entire design has existed as files on a computer and perhaps as a prototype on an FPGA. Now, the design is considered taped out, which is an industry term meaning it's finalized and sent for manufacturing. This finalized design is handed over to a specialized partner called a foundry. If you look at the right side of the diagram, you'll see this stage is handled by the foundries, who are experts in chip fabrication. Think of companies like TSMC or Global Foundries. These are not the companies that design the chip. They are the manufacturing plants that build chips for other fabless companies. The foundry takes the design files from the fabless vendor and uses them as a blueprint to begin the incredibly complex process of semiconductor manufacturing. This involves hundreds of steps, using light to etch patterns onto silicon wafers, layer by layer, to create billions of transistors and the wires connecting them. This process creates many identical chips on a single large, thin disk of silicon called a wafer. The term volume is crucial. We're no longer making just a handful of chips for testing. We are now manufacturing them in large quantities, thousands, hundreds of thousands, or even millions. This is essential for the business model of most electronic devices. The huge initial cost of designing the SoC is spread across all these units, which brings the cost per chip down significantly. After the chips are fabricated, they are tested while still on the wafer. The wafer is then cut up or diced into individual chips. Each working chip is then enclosed in a protective package, which also provides the electrical connections, like pins or balls, to connect it to the rest of a system. Finally, the ship part of this step means these packaged and tested SoCs are shipped from the foundry to the next company in the supply chain. Looking down the flowchart, that next company is the device vendor, who will take on the PCB manufacture and device assembly. So, the foundry's job ends here, and the final product manufacturer's job begins. This step represents a massive commitment. Once you start volume manufacturing, it is extremely expensive and time-consuming to go back and fix a bug in the hardware. This is why all the preceding simulation and verification steps are so vital. You have to be as certain as possible that your design is perfect before you press the Go button on manufacturing. We've now reached the very last stage of our SoC design flow, which is highlighted here: PCB manufacture and device assembly. So, what does this mean? Think about it. All the previous steps, from designing the chip, simulating it, and even getting it physically fabricated by a foundry, have resulted in a tiny, powerful silicon chip, our system on chip. But a chip by itself is like a brain without a body. It can't function on its own. It needs power. It needs to connect to other components like memory, a screen, buttons, and so on. This is where the printed circuit board, or PCB, comes in. You've probably seen one if you've ever looked inside any electronic device. It's that green board with lots of tiny metal lines and components soldered onto it. Those metal lines are like the nervous system, connecting everything together. In this PCB manufacture and device assembly step, our newly fabricated SoC is taken and mounted onto a custom-designed PCB. Along with the SoC, other necessary components are also placed on the board, things like RAM chips for memory, flash memory for storage, connectors for USB or HDMI, power management circuits, and anything else the final device needs. This whole process of putting the chip and other parts onto the board and soldering them in place is the device assembly part. If you look to the right, you'll see this stage is handled by device vendors. These are the companies that make the final products you and I buy. Think of companies like Apple, Samsung, or Dell. They take the SoC, which might be designed by a fabless vendor like Qualcomm and made by a foundry like TSMC, and assemble it into a smartphone, a tablet, or a laptop. They put the assembled PCB into a case, add a battery, a display, and speakers, and create the complete, finished product that ends up in our hands. So, this is the final, crucial step that transforms our complex, abstract design into a tangible, functional electronic device. It's the bridge between the world of chip design and the world of consumer electronics. We've covered a lot of ground so far, haven't we? We started by looking at the motivation behind the SoC design framework, understanding why it's so important in our post-PC world. We then moved on to weigh the pros and cons by discussing the advantages and limitations of SoCs. After that, we took a detailed look at the SoC design flow, seeing how a chip goes from an idea to a final product in our smartphones and tablets. Now, as this outline shows, we're about to dive into the next major topic, which is highlighted here: programmable SoC, or PSoC for short. This is a fascinating concept that blends the world of traditional, fixed-function SoCs with the flexibility of programmable hardware. Remember when we talked about the limitations of SoCs, like their lack of flexibility after being manufactured? Well, PSoCs offer a powerful solution to that problem. We're going to explore what they are, how they work, and why they are becoming so crucial for prototyping and for creating adaptable electronic systems. Let's move on and see what makes these programmable systems tick. This page introduces a really powerful concept: the programmable SoC, or PSoC for short. Before we dive into the details of a PSoC, Let's look at the first point. It mentions that SoCs can be prototyped and tested on FPGAs. So what is an FPGA? It stands for Field Programmable Gate Array. You can think of it as a blank chip filled with millions of tiny, unconfigured logic blocks, almost like a huge box of digital Lego bricks. As a designer, you can write code that tells these blocks how to connect and what to do, allowing you to create any custom digital circuit you can imagine. This is incredibly useful for prototyping because if you make a mistake in your design, you don't need to create a whole new physical chip, which is extremely expensive and time-consuming. You just reprogram the FPGA, and you can test your new design in minutes. Now, if you want to build and test a complete SoC using one of these FPGAs, this slide tells us there are two main ways to do it. The first option is to use what we call a soft core processor. A soft core isn't a physical piece of silicon. It's a processor design described entirely in software code, like a blueprint. You take this blueprint and use it to configure the FPGA's generic logic blocks to act like a processor. You're essentially building the CPU from scratch using those standard digital Legos. The communication bus that connects this soft processor to other parts of your system is also implemented using the FPGA's configurable wiring. The second, and often more powerful, option is to use a modern programmable SoC, with the Xilinx ZYNQ family being a prime example. These devices combine two things on a single chip. They have a hard processor, a real, physical ARM processor that is permanently etched into the silicon for high performance and low power consumption. This is like getting a specialized, pre-built high-performance engine in your Lego kit. This hard processor is then connected to the second part of the chip, the programmable logic fabric, which is the traditional FPGA blank canvas area. This connection is made using a high-speed, standardized bus, like the AMBA AXI bus. This approach gives you the best of both worlds, the guaranteed performance of a dedicated processor for running complex software, and the total flexibility of programmable logic for creating your own custom hardware accelerators and peripherals. So, why would we want this programmability? The last point on the slide gets to the heart of it. PSoCs can overcome some major limitations of traditional ASICs. An ASIC, or application-specific integrated circuit, is a chip designed for one purpose and cannot be changed after it's made. Think of the main chip in your smartphone. PSoCs offer two huge advantages over ASICs. First, they provide flexibility. Because part of the chip is reprogrammable, you can actually modify the hardware functionality later on. You could fix a hardware bug or even add a new feature by sending out an update that reconfigures the programmable logic. This is something you could never do with a fixed ASIC. Second, PSoCs lead to a faster time to market, especially for products with low to medium production volumes. Designing and fabricating a custom ASIC is a very long and costly process. For many applications, it's much faster and more cost-effective to use an off-the-shelf PSoC and simply program it to meet your specific needs. This diagram shows us the fundamental architecture of a programmable SoC, or PSoC. As you can see, the architecture is split right down the middle into two main parts: the processing system, which we call the PS on the left, and the programmable logic, or PL, on the right. Let's start with the processing system. You can think of this as the hard section of the chip. The components here are fixed. They are physically etched into the silicon during manufacturing, just like in a standard microprocessor or microcontroller. At the very center of the PS, we have the brain of the operation, the microprocessor, which in this example is a powerful ARM Cortex-A9. This is where your software, like an operating system or your application code, will run. Connected to this microprocessor, you'll see a memory block. This is for storing the program instructions and the data that the processor needs to work with. Below the microprocessor, we have a block for hard silicon peripherals. These are standard, pre-designed hardware modules for common tasks. Think of things like USB controllers, Ethernet ports, or basic timers. They're called hard because their function is fixed and cannot be changed by the designer. Now, how do all these parts in the processing system talk to each other? They use the bus labeled AXI. AXI, which stands for Advanced Extensible Interface, is a high-performance communication standard. It acts like a highway, allowing the microprocessor to quickly and efficiently exchange data with the memory and the hard peripherals. So, that's the PS side, a complete, standard processing system. But the really exciting part is on the right, the programmable logic, or PL. This is the soft part of the chip. Think of it as a blank canvas of logic resources that you, the designer, can configure. It's essentially an FPGA, a field programmable gate array, living on the same chip as the processor. Inside this PL section, you see blocks labeled custom peripheral. These aren't predefined. You get to create them. Do you need a special kind of video processing unit? Or a custom accelerator for a machine learning algorithm? You can build that hardware logic here in the PL. This gives you incredible flexibility and the ability to accelerate tasks in hardware, which is much faster than doing them in software on the processor. The most critical feature in this whole diagram is the bridge between these two worlds. Notice the main AXI bus that extends from the processing system over to the programmable logic. This connection is key. It allows the software running on the ARM processor in the PS to communicate directly with the custom hardware you've designed in the PL. The processor can send commands to your custom peripherals, read results back, and share data. So, in summary, the architecture of a PSoC combines the stability and software friendliness of a traditional processor system with the immense flexibility and performance of custom hardware logic. You get a hard processor to run complex software and a programmable fabric to create specialized hardware accelerators, all tightly integrated on a single chip.